simple compensator design using the argument principle. Okay. Now, what are we doing here? Argument principle. Okay, what are we doing here? So we are looking at compensators of the form s plus a over s plus b. For example, s plus 1 over s plus 10. All right. For small s, it is about 1 over 10. Large s, it is about 1. In both cases, the argument or phase is 0, more or less. Okay, but for s between 1 and 10, like 3 or 3i, right? What happens is this is something like s over 10. Why is that? Because s plus 1 and s plus 10, the 3 is much smaller than 10 and the 1 is much smaller than s, something like this. So this is more like a derivative. A derivative anticipates future change, so it leads in phase. Okay, so when we make a Bode plot of this, what we expect is that the phase will look like this. So this is log of omega and this is the phase, and it won't go all the way to 90 because that's a perfect derivative. It won't go that far, but over here it will be close to 0 and over here it will be close to 0. That's what we expect. Let's make sure that that is indeed the case. So here is my MATLAB window. Let me say C is equal to TF 11 110, and you see that's s plus 1 over s plus 10. And if I make a Bode plot of C, you will see that the phase goes up to, more than 50 degrees. Okay, it goes up to 55 degrees or so. Okay, so this is what it is. The magnitude here is minus 20. That is because it was 1/10. The common log of that is minus 1. Decibel makes it 10, and then you multiply by 2. So that's minus 20 and 0, because for large s it is 1, as we have discussed here. For large s it is 1, so that's 0 dB. For small s it is 1 by 10, so that's minus 20 dB. Okay, good. Now let us look at this plant here, which as you can see is a negatively damped oscillator. If I look at the root locus of G, then I find that these poles here just go straight up. I want them to move inside here, and this C compensator should work. So in fact, if I do R locus C times G, in that case it will move in. Okay, now let us say I want this root locus branch to go through some point that I like. Okay, so for example, over here for a gain of 45, it is minus 2 plus about 4i. Okay, let's say I want it to go through minus 2 plus 5i. How do I design this compensator? I can design this compensator as follows. Remember that I want it to go through a certain point like minus 2 plus 5i, but the gain is still indeterminate. I will have to, for some gain, it will go through that point. And so although I am specifying two scalar values, right? I'm specifying a point in the complex plane. I'm saying it must go through. So suppose G is 1 over s square minus s plus, let's see what we had here, plus 6 C is equal to S plus A over S plus B, and we want the root locus to pass through -2 plus 5i due to design needs. Okay, so how do we choose A and B? It seems that we have two parameters to choose. You may think that there are two conditions to meet, but the gain k is indeterminate, so that adds a degree of freedom. In this way, there is only one parameter to meet, or one condition to meet. Okay, and so we will have one free parameter, as you will see. Okay, so how do we begin? We begin like this. We say that CG must have phase 180 degrees plus minus 360 degrees times n, right? So that whole circle doesn't matter, so it must have this phase here. All right, we have two poles here. Let's find those precisely. So we'll come here and we will say roots 1, -1, 6, and they are 0.5 plus 2. I'll just say 2.4. Okay, 0.5 plus 2.4 I. So this is 0.5 plus 2.4 I, and this is 0.5 minus 2.4 I, and my compensator has a 0 here and a pole here. Let us call this minus A, and let us call this minus B, which means this distance here is B and this distance here is A, and I want this root locus to pass through this point here, which is 2, and that height is 5. I hope this part is clear. Now, when the root locus point is here, I have this angle. Let me call it theta 1. I have this angle. Let me call it phi 1. I have this angle. Let me call it phi 2. And I have this angle, which is phi 3. Okay? All right. What I want is that theta 1 minus phi 1 minus phi 2 minus phi 3 is equal to 180 degrees mod 360 degrees, right? So this you must remember, because there is a plus or minus element over there. And now you see it is fairly easy, because phi 2 is equal to 90 degrees plus the tan inverse of this angle, right? So that is tan inverse of this distance being 2 and that being 0.5 is 2.5, and this being 2.4 and that being 5, this is 2.6. Okay, so let me figure out how much that is. 90 plus a tan 2.5 by 2.6 times 180 by pi. Okay, so that is 133.9. I will write 134. Okay, so 134. All right, degrees. How much is phi 3? Phi 3 is equal to 90 degrees plus tan inverse of, the horizontal extent is still 2.5. The vertical extent is now 5 plus 2, 5 here plus 2.4 here, so that is 7.4. Come here and I have .4, and that is 108.7. I will round up a bit and the other one I'll round down a bit. So 108.7, I'll make it 109. So over here 109. You realize it is perfectly possible to do it with 2 decimal places. I'm just taking fewer. How much is phi 1? Phi 1 depends on b. Alright, so now I have to choose some b. Let me choose b to be 8. So b is a free parameter. Choose b equals 8. We'll see if it works. Okay, so if we choose b to be 8, in that case phi 1 equals tan inverse. Now what is the vertical extent? The vertical extent is 5 and the horizontal extent is, this was 2, this is 8, so the horizontal extent would be 6. 5 by 6 equals, I come here to MATLAB and I say okay, so that is 39.8, but I will round down because I rounded up a bit over there. But maybe I won't. I'll just call it 40. Okay, so that's 40. All right. And so what do we need? What we need is, I'll move this here. So what we need is theta 1, right? So I have here theta 1. So what we need is theta 1 minus 134 minus 109 minus 40. And it is much easier to make this something like minus 180. So minus 180. And so theta 1 equals minus 180 plus 134 plus 109 plus 40 equals. Let's see how much that comes to. And that comes to minus 180 plus 134 plus 40 plus 109. Okay, all right. So that is 103. Okay, so theta 1 is 103 degrees. Which is equal to 90 plus 13. Okay, very good. So I come here and now I will use red, and basically it will be somewhere here, so that this angle is 103 degrees. Okay, so I'm making some small approximations in the angles. I hope you don't mind. So then 103 is basically 90 plus 13, and so over here, if this distance is, let me call it something h, and the vertical extent is 5, So what I have is tangent of 13 degrees equals h by 5. H equals 5 times the tangent of 13 degrees. So I come here and I say 5 times the tangent of 13 times pi by 180, and that's 1.15. Okay, so we come here, this distance is 1.15, this distance is 2, and therefore this is 0.85. Okay, all right. So that's our compensator. C equals TF 1.8518. Okay, it's a lead transfer function. Sorry, it's a lead compensator. The Bode plot of C, as you can see here, goes up. Okay, and the root locus of C times G comes in as we expect. Okay, and we can put a hold on, and then we can plot -2, 5 with a red circle to see if it lies on the root locus, and you see it does. The approximations we made were small, so it's good enough. Here, if we zoom in, we will see it doesn't exactly lie on it. That is because of the small approximations we have made. We can do a more accurate calculation. Okay, so this is how we can use a direct principle. Now, what is the gain we need? The gain we need we can find by coming over here, and the gain is 42, and so we will say C is equal to 42 times C. So that's the gain now, so the big gain. And then we can look at, for example, the step response of G, which is unstable, so it will grow. Hold off. We can look at the step response of G. That's unstable, so it was growing, right? You can see it's exponentially growing. But if we look at the step response of C times G by 1 plus C times G, you see it settles down quickly. Okay, if we put the compensator only in the feedback loop, the root locus stays the same, the transient response changes, and now it's actually a better behaved one. Okay, it saturates at about 0.95 or something. That's okay. I'm sorry, 0.095, and that's okay. We can use other methods to improve it, like we can just amplify the input first before we put it into the system. So although I have not drawn that in earlier lectures, but our control strategy may easily be something like this: U going in, then a gain K, and then we have, that's our plant, that's our output, that's our compensator, and then we would adjust this gain so that when we give it a unit input, it will stabilize at a unit output. It will oscillate a bit and stabilize at a unit output. Okay, we can also use lag compensators, which are if for example s plus 10 over s plus 2, this is a lag compensator, and there will be situations where we may like to use it. So let us say c is equal to so that's a lag compensator. For s about 4, it's something like 1 over s or 10 over s or something like this. So that's something like an integrator, so that lags. We can make the Bode plot of c, and we will see a phase lag. Okay, so you see there is a phase lag instead of a phase lead. You're not surprised. That's how it is. So now we can use the argument principle to design. Let me go back to the old one. Okay, we can go back here. Because I have multiplied by 42, it should now, for a gain of 1, it should be about, for a gain of 1, it should be about minus 2 plus 5i, okay, which you can see that it is. All right. What else do I want? I want you to understand that for more complicated systems there may be other branches which may not behave as you like. In this approach you can make sure that one root locus branch goes through the point that you are specifying, but of course if there are many branches, some of them may be in the right half plane by the time you achieve this, and then you will not get stability. Some of them may be very close to the imaginary axis, and then you'll get a long sustained oscillation, and that's a different matter. But over here at least you'll be able to get one branch of the compensator to pass through the point you want. We can take another example where we can say TF, we can say 1, 0, right? And then if we look at the root locus plot of G, so now there is a derivative on top, you see. So when we look at the root locus plot of G, it comes in anyway, all right, and then it sort of goes in over there. This point here is something like, let's see, this point here is 2. Minus 1.44 plus 2i, something like that. I may want it to go through minus 3 plus 2i, or I may want it to go through minus 1.44 plus I, so that it is better damped, and then the same principle can be used to design a compensator which will make one branch of the root locus plot, of the root locus, go through that desired point. That's all.